All right, velocity is a vector. So we talked way back when we were talking about vectors versus scalars. We talked that velocity is a measure of speed, so a magnitude, and direction. So it's basically how fast you're going and in what direction. So we're going to be using that, and I'm going to show you how vectors apply to velocity. And one of the key concepts, key topics here is what we call relative velocity. Relative velocity is how fast you perceive, as the observer, how fast you perceive an object to be traveling at. All right, so I have a bit of a chart set up here for us. So let's put the bus doing 80 kilometers an hour, the train at 100 kilometers an hour, and the arrows indicate the direction, and our car is doing 120 kilometers an hour. And in this chart, my location, I want to be on bus, on train, on the car, and side of road. And we want to talk about how fast things seem to be perceived. So I'm going to start at the bottom, actually, side of road. So this is you standing at the end of your lane waiting for the bus. And this bus goes flying by you. What do you perceive the direction, or how do you perceive the speed or velocity of the bus? Well, you perceive this bus to be traveling 80 kilometers an hour, in this case, to the right, and I get the direction from the arrowhead. Okay. The train then would be 100 kilometers an hour left, and cars that are passing 120 kilometers an hour, and that one would be to the right. So definitely not an Acura when we're talking about the 120 kilometers an hour. Okay, so now if I'm on the bus, so on the bus we're not worried about how you perceive things when you're on them. Okay, but if you're on the bus and you look out the window and you see the train, so all you can see is the train itself. How do you perceive the train? Well, if you're heading 80 kilometers an hour toward the bus, or in that direction, the train's coming at you at 100. Sorry, you're doing 80 on the bus. It actually looks like the train is doing 180 kilometers an hour to the left. Okay, because what your brain does, your brain fixes itself in its relative location, and it has the bus as stationary in your head. So when you see the train coming at you, you don't perceive the train doing 100 kilometers an hour. You actually see it doing 180 screaming at you. Similarly, if you look out the window when the train is running side by side with the car looks like it's just slowly passing the train, the bus. So if we end up with the bus and the bus doing 80 and the car doing 120 here, you see it passing by, so it's not actually perceiving it doing 120. Your brain translates it to doing 40 kilometers an hour to the right. So it's just gradually passing, so it's that difference. If you're on the train, however, and you meet the bus, it's the exact same thing. You perceive 180 kilometers an hour, but now the train is stationary, and it's the bus that's moving that fast. And if you're on the train and you meet the car, and you're at the front of the train, you see this car hurtling toward you at 220 kilometers an hour, and that would be to the right. So your relative velocity is basically a statement of where are you and how are you perceiving the object's motion around you. What happens if you're on the car? Well, the car, you pass the train, so it actually looks like the train is backing up. If you've ever been parked at a red light waiting and the car ahead of you is maybe a standard and starts to either creep back on you and you can't see the tires, or a vehicle beside you is either moving forward or backward, it gives you the perception that all of a sudden you think you're moving, so they have that disorientation. So if you're in the car and you're passing the train, it actually looks like the bus, my mistake, is actually backing up. So it's actually doing 40 kilometers an hour to the left, so it looks like it's backing up and you're stationary. It's funny tricks that the brain plays with you. Similarly, the car and the train, you see it doing 220 kilometers an hour to the left, and the car actually being stationary. Which leads me to the actual formula. So V relative, this is what we call our relative velocity. And this is another formula that you want to have handy. Not a very large formula. So this is your relative velocity formula. So V and then REL subscript is relative velocity. VA is the observer's velocity. The observer's velocity. So that would be you in the car, you on the bus, you on the side of the road. And VB then is the observed object's velocity. So whatever you're watching. Okay, so whatever you're paying attention to at that time. So observed object's velocity. Okay, and that's the equation. We're simply going to be rearranging it depending on what we're looking for when we go through and work on our examples. So I have 2 examples. I'm going to go through them in the final video, and then you're able to get going or started on the assigned work.